Okay. What we're going to talk about is called the chain rule. And what makes the chain rule hard is not the chain rule itself. The chain rule itself is actually easy. It's kind of related to what makes, for any problems in the quotient and the product rule, and that's knowing when to use the chain rule. When do you have the chain rule problem? And if you do have a chain rule problem, how do you tell which part to do first? So we're going to practice a little bit on that at the very beginning. So we need to talk about something first called composition of functions. And a composition of functions is basically where the input of one function is itself a function. For example, if the function is f of x equals x squared, and you put in x plus h, it becomes x plus h squared, then x plus h actually is a function on its own. So that's a composition of functions. You actually did some of that in 11.1. The outside function here is the fourth power function. It's what's on the parentheses. If you've got something in parentheses with a power outside of it, the power outside of it is almost always the outside function. What I think of as the outside function. And the inside function is whatever's inside the parentheses. Now it can also be something like a radical, where you had some kind of expression underneath a radical like x squared plus 2. And then the square root becomes the outside function. And that's what this one looks like. The square root sign, or the radical part, is what we call the outside function, or the g of x function. And then what's inside of g of x, its x value, is 2x cubed minus 6x. This is another composite function. The 5x squared isn't composite, it's just part of a product. But the second factor of the product is a composite function, because the outside part of it is the expression on the inside, and there's a power of 4 on the outside, and the inside of that power of 4 is x cubed plus the square root of x. So the first thing we want to do with this is we want to practice finding composite functions, because it'll be easier if you can find the composite function to figure out when the chain rule is going to come into play. So here we've got f of x is 2x minus 1. So what f's job is to multiply whatever you put in for x by 2 and then subtract 1 from the result. G of x's job is to take whatever you have for x and multiply it by 3 and add 5 and then take the square root of it. That's what their jobs are. It's kind of like their job description. So if I ask you, get back. If I ask you what is f of g of x, and that's actually the way that you say that, is f of g of x. Basically, g of x is taking the place of x in f. So what you want to do is you want to take 4x plus 1 and put it in for this x and put it in for that x. Let me leave the PowerPoint here for a second, and we'll go to the side here and actually work a few of these, because that's actually, I think, the best way to learn how to do these. Okay, this is G. G is on the outside. So G's job is to take a square root of 3 times whatever x is and add 5 to it. But whatever x is f of 4. So we have to figure out what is f of 4. Okay, f of 4 is 2 times 4 minus 1. 2 times 4 is 8, and 8 minus 1 is 7. So 7 goes into G. And then that means what we've got is G of f of 4 is equal to the square root of 3 times 7 is 21 plus 5, or the square root of 26. Okay? You found F, but you also found G. What we did was we took the 4 and dropped it in F, and F did its job. It said, okay, 2 times 4 is 8, minus 1 is 7. So here, there's 7, and it gave it to G, and G says, okay, you gave me 7, I'm going to multiply it by 2, and then add 5 to it and take the square root. And that's the way that it works, okay? The next one says, take f of G of 4. So the first step is, what is G doing to 4? Well, 3 times 4 plus 5, and take the square root of it, which is the square root of 12 plus 5, which is the square root of 17. So G does its job with 4. It says, okay, it's negative 17, or square root of 17, here you go. And then what F does with it, if you go back up and look at F's rule, F is going to take square root of 17, and multiply square root of 17 by 2, and subtract 1. So that's f of G of 4. So whatever's inside gets to work first. And then whatever's on the outside finishes the job. Okay? So what would G of negative 2 be?
Square root of 3 times negative 2 plus 5.
Mm-hmm. So it's the square root of negative 1, right? So then F's job comes along, and F says, whatever I've gotten here, take it and multiply it by 2, and subtract 1. And what I have in there is the square root of negative 1. So F's final answer is 2 square root negative 1 minus 1. and that's f of g of negative 2. Now, there is some notation that you're going to run across at some point, without a doubt. Let me just flip over on the back of this thing. This is always confusing for people. F of g of x is very often written as f o g of x. I don't like that notation. I think it's confusing. People see that little circle and think, oh, that means multiply, which I would too. So if you see that, this is actually what they mean. And I think this makes much more sense. Okay, here's another example. If f of x is equal to 2x squared plus 5 times x, and g of x is equal to 4x plus 1, find f of g of x. Now remember, g's job is to take whatever you put in it, multiply it by 4 and add 1. F's job is to take whatever you put in it, square it, multiply by 2, and add 5 times what you had to start with. Okay? This says F's on the outside. What we want to do is we want, in place of g of x, we want to put the actual expression, 4x plus 1. So what we're finding here is f of 4x plus 1. Knowing that what f does is it takes 4x plus 1 squares it and multiplies it by 2, and then takes 4x plus 1 and multiplies it by 5 and adds it all together. So that's going to be, actually, this is just fine. If you want to simplify it, you can. If you're going to simplify it, then you're going to have to do quite a bit of algebra. But really, this shows you exactly what it is better than anything else does. The only reason you would do this would be if you were trying to actually find the derivative of this and you wanted to check and make sure you've done it right, then you could do this and take the derivative of that and see if they matched. Anybody have any questions?
What did you cover the last 2 hours?
Last section. 2.3, the product and quotient rule, and I recorded it.
I was just looking through it a little bit.
Now, if you turn around and do the same thing, you're wanting to find g of f of x. For what g does is it takes whatever you put in it, multiplies it by 4 and adds 1. So what you're putting in it is f of x, and f of x is 2x squared plus 5x. That's it. And if you want to simplify it, you can, but you don't have to. I mainly want you to be able to show me how you plugged it in. Now, the next example, they're going to kind of switch it up on you a little bit. They're going to give you h of x, and h of x is actually f of g of x. But you got to figure out what's f and what's g. So taking g to be the inside, apparently what f's job is to square it, multiply it by 2, and add 5 times it. So the inside would be g of x, because that's the part that matches on both terms. So g of x is going to be 4x plus 5, or 4x plus 1. And then the part that's being done to that is f. So f takes whatever you give it, multiplies it times 2 after it squares it. Then it multiplies it by 5 and adds that to the first term. Okay? This is the part that's most important to be able to do, because what you're going to be given is something like this and asked to figure out what the other two functions are that were used to create that. That's what the calculus is going to require you to do. Since this is the most inside of everything, this would be g of x. And what's being done to g of x is that square root. So f is the square root function. And g of x is what's taking the place of x. Now, if you can do example 3 and figure out example 3, then you're not going to have near as much trouble with this chapter. Does anybody have any questions? Ready? Okay. I don't want to rush you, but we do need to get through. Now, I'm going to show you the chain rule, but I'm not going to expect you to memorize it or be able to explain it to me. There's the two different versions of the chain rule, but I'm going to give you the version that's in English. The version that's in English is take the derivative of the outside function times the derivative of the inside function. Okay? derivative of the outside times derivative of what's inside. And the only way to learn how to do it is to practice. If I gave you that function, don't worry about taking the derivative yet. If I gave you that function, what is the outside function? What's f? It's the power of 1/2. What's the inside function? Okay. So if I'm going to take this derivative, what I'm going to do is I'm going to take that 1/2 power and I'm going to bring that 1/2 power down in front and reduce it by 1, which makes it a negative 1/2, and that little u there just is whatever's inside there. Okay? And then the derivative of 3x squared minus 5x is 6x minus 5. And that's really all there is. So when we do the derivative, here's what it actually looks like. Bring the 1/2 power down in front for the square root. Reduce the power by 1/2. Keep what's inside the radical, what's inside the parentheses. Multiply the derivative of what's inside the parentheses times the whole thing. And what you wind up with is either this expression, which is just fine, you do not have to simplify it, or that one.
Can we work that one out by hand quickly?
Okay,
That whole modular, just good.
kind of blows you away.
Okay. Sorry, just wondering.
Okay. First thing we want to do, and this is the way, this is my way of explaining it, that's their way, and I don't know which one works best. Different things for different people.
Step by step.
Okay, first thing you want to do is you want to find f of x, because remember it's always f of g of x if it's a chain rule. Okay? So the first thing I want to do is find f of x. And what I see f's job as being is that. Right? It's the outside. G of x is the inside. If you take the derivative of the inside, the derivative of the inside is 2 times 3 is 6x minus 5. Okay? But since this is the outside, what I need to do is I need to bring the 1/2 out front and reduce that power by 1, which makes it negative 1/2. But I leave g of x inside of it. Okay? Derivative of the outside, derivative of the inside. Done. You're finished.
That's it.
That's it. Now what they did was, because this power was negative, they pulled it down in the denominator, and because the 2 was in the fraction, they pulled it down in the denominator, but this works just fine. My math lab will take it that way. Your calculator loves it that way. If you've got to plug in a number for it, your calculator doesn't mind a bit. It's got all those parentheses and stuff.
Okay.
Okay?
Still a little fuzzy on how you got that. Like, I know you took the 1/2 from up top, like,
Mhm.
and moved it down there because that was the power.
Right.
And then you just plugged in what's on the inside.
Yeah, leave it alone.
What's the negative 1/2 for at the top? Like, how come that's?
1/2 minus 1.
1/2 minus 1, okay, thank you.
Okay?
So I was like, wait a second.
Okay, yeah, because you're still getting used to power rule, and that's the power rule. That's what that is.
A little lost.
Okay?
Yeah.
All right, let's try another. Find the derivative of this problem. What's f?
Okay. 8.
Okay, so it's the 8th power thing. So we're gonna take whatever's in the parentheses, bring the 8 down in front of it, and do 8 minus 1. So we're gonna wind up with 8 times whatever's in those parentheses to the 7th power. Okay? What's inside? X squared plus 5x. What's the derivative of what's inside?
X plus 5.
2x plus 5.
Yes,
You're done. That's all you have to do.
Yeah, like my math, but I don't know if it's gonna be that easy. And on there, like I hope you're good.
As long as you get this part correct and you're very careful how you type it in, it will take this. Some of them, it'll, if you click ask for an example or something, it's gonna make you do all the simplification. That's algebra. I don't care if you do the algebra or not. Do the calculus, okay? Get the first step. And if it fusses about it, ask my instructor. Now this is back off of the PowerPoint. A common error is to forget to multiply by g prime of x when using the chain rule. In other words, that step right, and I'll actually do this for you most of the time when I'm doing these, is I'll point out that this is where that came from. Okay, that's always your second step, and that's the step a lot of people leave out. So be careful about that. It's a chain. It's a product of two derivatives. And g of x stays unchanged. When it sits in parentheses, it doesn't change. Only when you take its derivative, and it can't change till it comes out of the parentheses, which is when you take the derivative. So the thing to remember here is the chain rule is a two-step process. So our next example, and this is going to mix last chapter and this chapter, so you're going to have to be careful. This is a product. Okay? Your product is 4x times 3x plus 5 to the 5th. And you know that when we have a product, that you have to have the derivative of both of your factors. Now the derivative of 4x is easy. It's 4. The derivative of 3x plus 5 to the 5th is a chain rule. So you're going to take 5 times the parentheses raised to the 4th power. Leave the 3x plus 5 inside, but take its derivative and put it on the outside. Oh, sorry. And then keep in mind, on this particular one, that it would probably be easier to say 5 times 3 is 15 when you have to use it. So you got your derivatives now. So then the way that you do the product rule is first, which is 4x,
You can't see it, right?
let's see if I get it all on the screen. First times the derivative of the second plus the second times the derivative of the first, which is 4.
Those are fun.
Yeah, they're a little ugly. Nah, I'd say they're a whole lot ugly. Okay?
Remember all the rules stuff.
Now, it will look a little bit better, and you are less likely to make mistakes typing it in if you see something that you can easily simplify. The only thing you can easily simplify here is this. 4/15 is 60. X, then keep 3x plus 5 to the 4th power plus 4 in front would probably be easier to keep track of it, times 3x plus 5 to the 5th power. And I'm going to warn you, if you ask it to show you how to do that problem, it's going to go 4 more steps. It's going to try to factor out 3x plus 5 to some power. Don't pay any attention to that. Put that in. You don't have to have all that other stuff. Stop right there.
My math lab stop there.
Yes, well, the explanation won't, but my math lab will be happy with that. That's the only danger to using the show me an example or help me solve this, is that those two on this chapter, they'll make you go 4 or 5 extra algebra steps that you don't really have to have.
I just wish they'd learned to put the calculator steps in.
I've never been able to get them to
Yeah,
add.
like, I mean, Pearson really needs to work on that, or else Northeast State needs to find a company that has it to where it has the calculator instructions in there for the math classes.
We can add them in, but that means we have to go in and build them all ourselves, and because of the way that it does it, you know, we can't do every iteration of the problem. You may get stuck with something that's different from what we put it in there for. Okay, can you handle this?
Hopefully.
Hopefully you're gonna practice. Okay. This is a quotient rule, right?
How can we look at it and just know what rule it is? Like, I get it because the y equals is already there on that one, but this one, like, how am I supposed to know that's just a quotient?
Because it's a quotient.
Okay,
It's a fraction.
okay, so just because of that,
And you know this is product rule because it's 2 factors. It's multiplying. Okay? Because that's a quotient rule, then you're going to need to use the rule where you take the denominator and square it, and then the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So what that tells me I need to do is I need the derivative of x minus 1, which is just 1,
why would that just be one? Like, I mean, I'm sorry.
1x. 1 times 1x to the x comes out to the 0.
Okay, I thought I seen that
It starts out at 1. Your power rule says take the power, which is 1, drop it down in front, and then subtract 1 from it. But what's 1 times 1?
Well, what's mine?
What's 1 minus 1? 0. What's x to the 0? 1. So it's just 1. It will be the same if it was 3 x to the 1 minus 1. You would bring your 3 down in front. And 3 minus 1, except now the x doesn't disappear. It's 3x squared. But when it's x to the first power, when you subtract 1 from the first power, it disappears.
Well, then would you plug it back in and put 1 minus 1? Or that just, even though that says x minus 1, it's still just gonna equal 1?
It's just, its derivative is gonna be 1 because the derivative of the
Okay.
minus 1 is 0,
I got it.
okay? Now, I also need the derivative of the numerator. But in the numerator, I have a set of parentheses with a power on the outside of it. So when I take that derivative, I'm going to have to take that set of parentheses, bring the 7 down in front, subtract 1 and make it 6. And then take what's inside the parentheses and take its derivative, which fortunately is just 3. So 7 times 3 is 21 times 3x plus 2 to the 6th power. And this is n prime. Okay? This was d prime. So when I go over here and plug these in, then I'm going to plug them into the quotient rule. So when all's said and done, I'm going to take the denominator, which is x minus 1, and I'm going to square it. Then I'm going to take that denominator, which is x minus 1, multiply it by n prime, but here's n prime. And then I'm going to subtract the numerator, which is this, raised to the 7th power, and multiply it by the derivative of the denominator, but the derivative of the denominator is just 1. And you could actually stop there.
The derivative of the numerator, I don't see making.
The 7 times 3,
Oh,
okay? Anybody else not see something? Actually, I would need one more thing here. I would need one more set of parentheses after that to close this one up. Be sure you close all your parentheses. Questions?
Yeah.
Not yet?
Okay.
Okay. Let's try example 9. City revenue. The revenue realized by a small city from the collection of fines from parking tickets is given by this quotient rule, right? N is the number of work days each day and can be devoted to parking, that can be devoted to parking patrol. At the outbreak of the flu epidemic, 30 work hours are used daily in the parking patrol. But during the epidemic, the number is decreasing at a rate of 6 work hours per day. How fast is the revenue from parking fines decreasing at the outbreak of the epidemic. Now, there's nothing about the functions that are that difficult. The harder part of this is figuring out how to set up that problem. Okay, it says how fast is revenue? How fast? And how fast is it decreasing? Those words should trigger that I'm looking for a derivative, a rate of change. I need a derivative of something. What you want to do is you want to take the derivative of revenue with respect to time. And we're going to have to write it as a quotient rule. Okay? I'm going to leave it there for a second. Remember, all you're doing at this point is you are taking the denominator of your revenue function, which you've got there on paper in front of you. The denominator of your revenue function is n plus 2. So you're going to put it in the denominator and square it. Then you're going to take n plus 2 and multiply it by the derivative of the numerator, and the derivative of the numerator is just 8,000. Then you're going to subtract the numerator, which is the 8,000n, times the derivative of the denominator, but the denominator is n plus 2, and its derivative is just 1. And if you actually multiply all of this out, you get 8,000n plus 16,000 minus 8,000n, so actually the n's all drop out, and you wind up with just 16,000 over n plus 2 squared. Okay? Straight quotient rule. No chain rule at all at that point. And then since 30 work hours were used at the outbreak of the epidemic, that means n would be 30. So now that you've got the derivative, plug in your 30 hours for n into your derivative, and it tells you that the derivative's value is 15.625. And if you go back to the next to the last sentence in the problem, and it says during the epidemic the number is decreasing at a rate of 6 hours per week. So the derivative of n with respect to t is -6. So we're going to take this first derivative times the second derivative and figure out the revenue. So what basically, make sure everybody understands, what this is giving you is the rate at which your revenue is decreasing. And this is the rate at which it's decreasing. This is the rate at which your number of work hours is decreasing. And that product will give you the amount of revenue being lost, because this is how much per hour, and that's how many they're losing for each unit. So it's costing them about $94 a day at the outbreak of the epidemic. That's because people are staying inside with the flu, which we know all about, and so they're not parking in the parking lot. And they're not getting any parking fines. Okay? I don't hear anybody asking any questions, but I don't have the feeling you're understanding either, so. Can you tell me where maybe you don't?
I think I understand how to do it, it's just getting me flipping back through the notes and step by step
Okay.
to understand which ones, what rule I'm supposed to be doing whenever I'm supposed to be doing it.
Okay.
I'm gonna have to go step by step, but I mean, it seemed easy the way you explained it.
Yeah, the way, the actual derivatives in this case are not hard, it's being able to pull the information out of the problem.
Yeah, forget story problems, that'll be past my instructor.
Okay.
I'm prepared with that one, I might be able to, but setting it up. doesn't look the same.
Okay. I'll expect questions on them then. Okay, let's get the last one out of the way. It's compound interest problem, so hopefully it makes more sense. Suppose you have a sum of $500 deposited in an account with an interest rate of R% per year, and it's compounded monthly. There's chapter, 5 coming back to haunt you? And at the end of 10 years, the balance in the account is given by A equals 500. Remember, this is just your compound interest formula. $500 is your initial deposit principal times 1 plus the rate over 1,200 because it's 12 months a year for 10 years. And it's going to be for 120 because your interest rate is, I'm sorry, because it's 12 months over 10 years. One of those is not right. Yeah, I'm thinking the R isn't over 1,200. The R should be over 120. I love it when I clip something out of the book and it doesn't look like it's supposed to.
You love it when my stat lab doesn't look like the examples. Yeah.
Okay, let's see if I can find that problem. I want to know, I mean, it has, I have pulled up, honestly, people, I feel your pain because I've pulled up the instructor's manual and I find where they've made awful arithmetic mistakes in the 10th edition of the instructor's manual. You know, why did you not catch that before now? Come on, you can do it. Okay. Why is that 1,200? I'm gonna have to go look at that. Okay. Assuming that the 1,200 is right, and I'm not yet convinced that it is, you do know that compound interest does increase on a curve because it's got an exponent, it's not linear. We would need to find DADR, which if this is in fact right, as I said, I'm not convinced it is right now, the way you take the derivative is here's your chain rule. The inside function is 1 plus R over the 1,200 that I think ought to be 120. And then the power is the outside part. And the 500 is just a multiplier, is all it is. So if I'm gonna take this derivative, I bring the 120 down in front of the 500. And I reduce the 120 by 1, making it 119. And then I put the parentheses, I put their guts back in there, I put the inside function back in. And then the derivative of 1 is 0. And the derivative of 1 over 1200 R is 1 over 1200. And by the time you multiply 120 times 500 and divide by the 1200, that's where they came up with the 50. That I'll agree with as soon as I figure out where the 1200 came from. So when you do all of that, you just plug in the value, R is equal to 5. And that turns out to be $82.01 per percentage point, or if R is equal to 7, then it's $99.90 per percentage point. I'm sure at this point your brains are about fried, so. That's the last problem for that section. So we are finished with 12.2 and 12.3. And we will do 4 and 5 next time. I think that's all there is. Yeah, 4 and 5. Okay? Do not work too far ahead, although I'm pretty sure I don't need to even tell you that. I'm probably going to see if I can trim back in 13 and 14 a little bit so that we'll have more time for chapter 15. We may only do one section in chapter 14, and we may cut way back in chapter 13. There's only one section we have to do in 14. If anybody that didn't get to look at your test